Okay, so folks, here's the quick little presentation on the structure of the atom. Now, I'm sure you know a little bit about the structure of the atom with the idea of protons, neutrons, electrons, and different particles. But you probably don't know how they were discovered and how it all came about. So this is what this lesson is about. So first thing first, it all started with a gentleman by the name of J.J. Thomson. And he was the one who originally discovered the electrons. And the way he did this is by the cathode ray tube. So I'm going to have you watch a quick little video on this so that you have an understanding of what's going on, and then I'll describe what the experiment really showed in the end.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
So what does this all really mean? Well, here's the thing. His observations was that the rays bend in a magnetic field. That meant that it consists of charged particles. What he also found is that rays bend towards positive plates in an electric field. That means it consists of a negative particle. And here's the big thing. He used a bunch of different types of cathodes, meaning different types of gases. So he found that all of these particles were found in matter. So this is kind of a big deal because now they realized that the atom was actually made of more than one particle. It wasn't just a ball of something. It is just made of a bunch of different particles. And now it's a negative one they know of, the electron. So Robert Millikan came into this and furthered the information about the electron by determining its mass. He came up with an extremely clever experiment by using oil and a device that allowed for the control of electric charge, so he could determine the mass of an electron. So let's watch his experiment.
In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing a droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
So Robert Millikan was able to determine the charge of an electron as 1.6 times 10 to the negative 19 coulombs. And from that, because he knew the mass of the oil, he was also able to determine the actual mass of an electron, which is 9.1 times 10 to the negative 31 kilograms. Now, you have to think about this. This was at a very unique time because of the fact that there was very little technology available. You can see the contraption there on the left-hand side. It's a pretty crude device, but it was able to determine the mass of an electron. And they knew that these particles of matter were extremely, extremely small. So this led to two inferences. They know that atoms are electrically neutral, so therefore they must contain a positive part. The reason they knew they were electrically neutral is because we don't go around worrying about if we're going to get shocked by every single thing we touch. Secondly, the mass of an electron is so small, there must be other particles which contain most of the mass. So, because of what was known by Robert Millikan's experiment as well as J.J. Thomson's experiment, J.J. Thomson came up with the first idea of a model for the atom. He called it the plum pudding model. Basically, he suggested that the atom was a ball of positive charge, not a particle, but a ball of positive charge with electrons scattered within it. He knew that they were the particles. So if you look at the diagram there, that funny looking bread stuff that I found online, it's basically bread embedded with raisins. And the raisins represent the electrons, and the bread itself represents the ball of positive charge. So a group of scientists who worked under Thomson were on a mission, and what they wanted to do is really determine the structure of the atom. They didn't think this was the structure, and if it was, they had an experiment to determine it. And so a team led by Ernest Rutherford discovered the proton and the nucleus of the atom by using what's called the gold foil experiment. So here's what he did. He took a thin sheet of gold foil, and what he expected was this. He was going to shoot alpha particles at it. Now, an alpha particle would be like a ping pong ball. And the electrons, because the alpha particle would be like a basketball, and the electrons would be like ping pong balls. So what he thought is when he shot this alpha particle, which was much larger than the electron, it should shoot straight through. And the only reason why they were able to do this experiment is because of this amazing discovery of radioactive particles. And these alpha particles were these radioactive particles. So let's watch this short little video to describe Ernest Rutherford's experiment.
Ernest Rutherford, with Hans Geiger and Ernest Marsden, discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
So Rutherford's experiment with these alpha particles and having them deflected showed that there was a very large, dense mass within the atom itself. And so therefore, he's credited with the discovery of the nucleus. Now, at this time, they kind of had the idea that the protons were in the nucleus. And the quote is in his paper, he says, it is as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. They never expected this to happen. So the structure of the atom then changed, and Rutherford came up with his own model. And you can see this model here in the picture on the right-hand side. You've got the protons in the center, along with the neutrons, and the electrons scattered throughout. Now notice, the electrons are not moving. They're just kind of scattered around randomly. And the big thing is that most of the atom is made of just simply empty space. So this still didn't solve the problem with regards to mass. It wasn't until 1932 when Chadwick had discovered the neutrons of the atom when studying radioactive material. And he figured out the particle of the neutron. Therefore, now we have the structure of the atom with the nucleus and the protons and neutrons in the nucleus and the electrons scattered about. But if you've got protons near each other in the nucleus, how is it that they can even exist? Well, that's all because of nuclear forces. The attraction of neutrons to protons and neutrons to neutrons is stronger than the repulsion of the protons. And so therefore, they are able to hold each other together within the nucleus. Now, they have to be in a certain ratio in order for that to happen. So that's the key. And we're going to discuss this later on.